Hi all. Uh, the last videos we saw how do we close the Reynolds stress equations using some classical models. So we saw that classical models there are some four different types. Zero equation model where we don't add additional equation to the Reynolds equation. Two equation model K epsilon where we have two separate PD equation, one for K and one for epsilon. And the third one is Reynolds stress equations model where we have six additional equations for each of the Reynolds stresses. So algebraic stress is nothing but algebraic expression for the Reynolds stress in addition to the K epsilon model. So in this video we see how those zero equations models and K epsilon models are utilizing this constitutive Newton's law. Similar to the Newton's law of viscosity, we express the turbulent viscosity, and the turbulent viscosity is somehow has to be calculated. So in this video we see that a zero equation model, also called as mixing length model. So this mixing length model uses an algebraic expression to compute the turbulent viscosity. So kinematic turbulent viscosity. So based on the length scales, we know that turbulent viscosity has a dimension of meter per second. So we can approximate multiplying with velocity into and length scale term. So it becomes meter per second. Velocity scale have meter per second and length scale have meter. So multiplying to will give you the meter square per second. So that proportionality constant will be a this C term. So when we coming into the kinematic viscosity, then the rho will be added, density will be added to the right hand side. So this will be the expression for the turbulent viscosity using the algebraic equations. So this length scale will be something related to the eddy scale, large eddy scale, which is a characteristic length scale of the flow domain. How about the velocity scale? Velocity scale is something can be approximated through this length scale, which can be computed from the flow domain flow problem. And the other terms which up here is the velocity gradient, so which will give, and this proportionality will be closed by this additional constant called C is a dimensionless constants. So when we substitute this expressions into this, so we ended up with two CC values and also some kind of length this flow gradient. So then the totally will be this L square and this whole C, this all will be observed into a single new length scale called LM. So that then this kinematic viscosity can be modeled as Lm square into the flow gradient. So when you coming to the Reynolds stress equations, it is related to the dynamic viscosity, and that will be ended up with this flow. We ourselves know that will be related to the constitutive relations like kind of proportional to the flow gradient, and the proportionality constant is the turbulent viscosity. That turbulent viscosity is modeled by the kinematic viscosity into the density terms from 3.28 to 3.29. So this ultimately we have this flow equations, and the only thing the unknown here appear is the Lm. So this is the unknown constant that we needed to model, and which changes from every flow domain. And similarly for the scalar transport equations, we have turbulent diffusivity term which has to be modeled. We know the Prandtl number is somehow related by these expressions. So we have for various flows, we have some empirical constant values. For near wall flow it's 0.9, 0.5 for jet, and 0.7 for axisymmetric. Using those and the way we compute this turbulent viscosity, we could be able to identify the turbulent diffusivity for the scalar transport equations. So using some empirical and have done various experimental analysis for the two-dimensional turbulent force, people have identified some empirical values using the characteristic length scale of that particular flow domain. For example, mixing layer has 0.07 of the length scale, and jet have this one. These are the boundary layers, and this somehow we will come later part of this video, not what is a log layer, what is viscous layer. These are some of the thin layers appearing near the flow boundary, and this y and k is something. K is a one common constant of 0.41, and y represent the distance from the wall. These are very thin small values where there is a large flow gradients along the cross stream of the directions. Above that there will be a free stream. So these are the thin boundary layer appear near to the wall domain. So using this empirical analysis, we could able to identify the value of Lm that closes the Reynolds stress equations using that constitutive relations between the Reynolds stress and the flow shear rate of the things. So these are the advantages and disadvantages of this using the mixing learner. One thing is it have a good predictions for a particular flows. Very important flows like jets, mixing layers, boundary layers are well established theory because they have some empirical. People have conducted various experiments in the lab and try to approximate what would be the best things, and it is an universal applicability. It is very generality, so it is only depend upon the characteristic length scale of the domain, and these empirical constants are identified for a different particular flows. And once the unknown flow is taken, we will try to identify which particular type that flow belongs to, and the characteristic length scale that we can identify from the flow domain, and we can able to identify this Lm value. From once the Lm value identified, then we can compute the kinematic turbulent viscosity, and then the flow gradient itself will try to close the Reynolds stress, which will effectively we can solve the Reynolds equations. So this is the concept behind using this mixing length theory. But there are some incapacities of this algebraic model where it fails to capture those turbulent effects in flows with having large separations and recirculations, and it only tries to approximate the mean flow properties and shear stress. The other important things like mixing things are couldn't be able to capture by this model. But later in the next video we'll try to see how for the next sophisticated model of k epsilon using additional two PDE equations, one for k and another for epsilon, can overcome these limitations of the algebraic mixing length model. Thank you.